Hey everyone, welcome to hardwear.io webinar. I know it's a Friday evening, but thank you so much for joining us today. I'm sure this webinar is going to be very insightful for you all. Before we start, some quick announcement. We have announced our speakers for the upcoming hardwear.io conference, which is scheduled on the 1st and 2nd of October. I'll be sharing the link in the Zoom chat later. Please do join us. We have some really cool new research being presented, which has not been published before. Open source hardware design is growing popularity, and in some cases, it's the future of IoT world. Today we have Dhruv Fustini, who is a hardware designer and embedded Linux developer. He's on the board of Open Source Hardware Association and BeagleBone Foundation. Dhruv, being an ambassador for RISC-V, is going to talk to us today about the way forward to build a more transparent and trustworthy root of trust chips and other security projects that benefit the open source design at chip level. For those who are new to hardwear.io webinar, if you have any questions for the speaker, please do send it across via the Zoom chat. They will be answered after Dhruv finishes his presentation. So without any further delay, let's welcome Dhruv to present his session.
Hello.
Dhruv, over to you.
Yep. All right, let me share my screen here. Okay.
Yes, we can see the screen. Perfect.
Awesome. Cool. Let me minimize the Zoom window here. All right, yeah. So my name's Dhruv Fustini. Already had a bit of an intro there. Real quick, I pasted this in the chat, so you can click on it there. If not, if you want to take a screenshot or try and write that down real quick, that's the tiny URL takes you to these. They're Google slides. So you click on that URL, you'll be able to pull up the slides because there's various hyperlinks in the slides. So you'll be able to click on all the links as I go through the presentation. So I already had a bit of an introduction there, but just to give a little overview, I'm an open source hardware designer for OSH Park. We're a PCB manufacturing service based in the US. Also part of the BeagleBone Foundation. So some of you may have heard of the BeagleBone. It's a small open source hardware Linux computer. I'm also part of the Open Source Hardware Association, or OSHWA. And one of the things you might want to check out is we have a certification program for open source hardware. So you can go to that URL there and you can fill out just a little bit of information about your project, like where your documentation is, what your license is, and you can get a little number back that represents that you've been certified as open source hardware. And I'm also an ambassador for the RISC-V International, which is a not-for-profit. You can click on that link there to find out more about the RISC-V ambassadors and also how to join. Basically, it's just people in the RISC-V community that are really passionate about the technology. So there are a bunch of RISC-V meetups around the world. Due to the pandemic, they're all virtual right now, but at some point they'll probably start meeting in person again. So the upside to all being virtual is you can pretty much attend any one that you want to. So some of the ones that I've attended so far this year were Munich in Bay Area. So if you click on that link there, risc5.org/local, you'll see there's a bunch of different ones, or you could just search for RISC-V on meetup.com. And one of the big events that's coming up is in December. It's the annual RISC-V Summit. So this is like the big RISC-V event for the year. You can get more information about registering on there. And because of the pandemic, it's going to be virtual. It was going to be in California, but now anyone that wants to can attend it from around the world. So talking about RISC-V, and RISC-V is an instruction set architecture ISA. So what is that? So an ISA is the interface between hardware and software. So for example, if we have a C++ program, we get that compiled into instructions for the microprocessor or CPU to execute. But how does the C++ compiler know what instructions the CPU will understand? That's defined by the instruction set architecture. The ISA is a standard or a specification. So it's a set of rules that defines the tasks at a really low level that the processor can perform. So some ISAs you've probably heard of are x86, which Intel and AMD use, or ARM. So you're probably familiar with these different ISAs, but both of those require commercial licensing. So if you want to use them, you need to get a license from one of those companies to use it, and that can be kind of complicated and expensive. So RISC-V is a free and open ISA. It started about 10 years ago. A group of computer researchers, computer architecture researchers at UC Berkeley were doing research into new types of computer architecture and accelerators, and they wanted to have an instruction set to base their research around. And they didn't want to go through the cost and length that it takes to get a commercialized, say, license like ARM or something like that. So they decided to just do their own design. If you want to learn out more about the history and some of the more details about behind the RISC-V instruction set, Kirst Asanovich is the professor that started the project. And every year he gives the State of the Union, so there's a link to the most recent one in there. And I've talked about RISC-V a couple of times, and sometimes I get the question, what's the 5? So real quick, first, the RISC means reduced instruction set computer. That just means that the instructions that the processor executes are relatively simple, that we push the complexity into the compiler. The most commonly well-known opposite to that, which is complex instruction set computer, is what the x86 instruction set is. So not really super relevant these days, but that is what RISC stands for. And then the V is actually a 5, Roman numeral, because it's the 5th RISC instruction set to come out of UC Berkeley. And then why do I say it's free and open? That's because the specification is actually licensed under a Creative Commons Attribution International license, which means that anyone that wants to can download the specification and use it. So what's different about RISC-V? It's not the first open instruction set. There's other ones such as OpenRISC and other ones before that. But what makes kind of RISC-V special, and why is it seen this large growth over the last several years? To start off, it's simple. If you compare it to something like x86 has this massive amount of legacy instructions in there. So it's, I've heard people joke like no one person actually knows all the x86 instructions. So it's really complicated and complex. So if you're wanting to do like specific research into processor design, you don't need all that overhead of a legacy instruction set. And this is the 5th instruction set out of Berkeley, and they took the insights that they'd gained from the previous generations over the decades and took that to do a clean design. So they didn't have to worry about any sort of legacy support. So they just did a clean separation between the privileged and unprivileged ISA. And the other important thing that they did was it's just about the instruction set. It's not defining microarchitecture or specific technology. So take that out of the specification of the instruction set means that as microarchitectures change and technology change, that's not entwined into the instruction set itself. So one of the ways that it does this is by being extensible through extensions to the instruction set. So the idea here is it goes from everything from like small 32-bit processors all the way up to 64-bit or 128-bit processors in the future. But a key thing here is that the stable base ISAs are frozen. So if you write a program for the base 32-bit instruction set, it'll still work on whatever fancy RISC-V supercomputer there is like 30 years from now. And then additional features are added through optional extensions, but it's not changing the original base. So we aren't going to end up with like, RISC-V B and C. The base stays the same, but then there's extensions that go along with that. And the other important thing here is that it's community designed. So while it started at Berkeley, there's now people from many other universities and in different companies and people from different organizations around the world that are all involved now. If you want to learn more about RISC-V, like the instruction set and all the details, because there's all these different extensions, this is a really great way to get up to speed. The book's only about like 100 pages, so you can get through it pretty quick. If you go to that URL there, risc5book.com, there's different translations into different languages as well. So RISC-V and Industry is probably, so industry is where we've seen kind of the biggest growth with RISC-V over the last few years. A lot of companies are embracing it. And I was talking about how it's modular and extensible. So the idea here is that it's the one instruction set that you'll need for everything from a microcontroller to a supercomputer. And as I was saying, the base instruction sets are defined for 32-bit, 64-bit, and even 128-bit, which seems kind of a little bit silly now, but we're looking at potentially having massive amounts of persistent storage that's byte addressable in the future. Also, 128-bit might be useful for certain security research, where we use higher bits in the address space to encode different security properties. And then there's extensions for everything from small embedded processors that are low power all the way up to like supercomputers with this new vector extension that's going to make it much more efficient to do higher end calculations. And while it was started at Berkeley, it's now controlled by an organization called RISC-V International, which is a nonprofit organization, and there's over 690 members. It's always growing right now from 50 countries. So this is different companies, universities, and other types of organizations, and also individuals. So if you want to, you can join RISC-V International as an individual for free of cost, and nonprofits can also join free of cost. And if you're a corporation, there's different levels of membership. One of the ways I've learned a lot about RISC-V over the last couple of years is from their YouTube channel. They have all the talks from previous events like the RISC-V Summit. So there's a lot of great talks in there that you can learn more. So one of the things I'm quite excited about is companies are going to be shipping devices with RISC-V cores in them. So NVIDIA actually already is shipping RISC-V cores in their GPUs. Now it's not doing the graphics part, but it's in there for doing things like system management. So they already are shipping RISC-V cores in products. And Western Digital is planning to roll out RISC-V controllers in all of its storage products. So there'll be millions of Western Digital products with RISC-V cores in them soon. One of the reasons companies are interested in RISC-V is it allows them to avoid the licensing fees and royalty fees that they have to pay when it comes to a proprietary instruction set like ARM. You know, in addition to just the licensing fees, there's also legal costs and also long delays. It takes quite a long time to do these licensing agreements with companies like ARM. So it adds more delay into the process. So RISC-V is an alternative where you don't have to have the cost or the delays due to all that licensing agreements. It also gives you the freedom to choose how you want to implement the instruction set. So RISC-V is just an instruction set, but how you implement a processor that runs those instructions is up to you. So that's the microarchitecture implementation. When it comes to ARM, only a few companies like Apple and Samsung and Qualcomm have ARM architecture licenses that allow them to do their own custom implementation. Otherwise, everyone else is just licensing the same ARM cores that all of their competitors are. And in addition to being able to implement your own microarchitecture, there's already several open source implementations of RISC-V processors that you can use. So from Berkeley to ETH Zurich has some very popular ones, and also Western Digital has open sourced up their cores as well. So there's a large number of open source implementations that companies can use. And probably one of the most important things here is that RISC-V has a critical mass of software support now. One of the biggest drawbacks to introducing a new instruction set is that you need to have support in all the software that you care about. So Linux and FreeBSD supports it, GCC, glibc, LLVM, Clang, FreeRTOS, Zephyr, which is another real-time operating system for microcontrollers, and also QEMU, so you can actually simulate all of this if you don't have hardware yet. If you want to find out the latest of whatever programming language or whatever certain piece of software, and if it's supported on RISC-V, you can click on that link there and it takes you to on the RISC-V GitHub account. They have a list that they keep of all the current software support. Another important thing with RISC-V is that it's being embraced, not just in the US or in Europe, but it's being embraced all around the world. And earlier this year, so originally there was the RISC-V Foundation, so it moved from Berkeley to the RISC-V Foundation, but the RISC-V Foundation was based in the US, and there were some concerns around US politics and how that would impact some of the international members of the foundation. So earlier this year, they moved it to Switzerland, and it's now called the RISC-V International. So same idea as the RISC-V Foundation, but it's just been reincorporated in Switzerland to remove any sort of political issues. Another thing that's important to note about RISC-V is there's several countries or nations like India that have decided that they're going to have initiatives to build processors based on RISC-V in their nation. And I think there's a desire here for countries to have sovereign control over their technology, and have processors that are designed domestically and manufactured domestically. And then another big place where there's a lot of interest in RISC-V is China. And I think one of the big motivations here is last year, US companies were barred from doing business with Huawei, which is a huge producer of technology equipment in China, and that's a big problem for them. So they're highly motivated to seek out their own solutions, and RISC-V gives them a good foundation to start designing their own chips around. Ultimately, ARM was deemed that they were UK based, so they could continue doing business with Huawei, but how long will that last? So I think if you look at companies in China, it's very much in their interest for them to develop their own implementations based around an open ISA like RISC-V. So sometimes I see people just conflating RISC-V with open source, and I think it's important to make kind of the distinction here. So RISC-V itself is just a set of specifications, a set of instruction set specifications that's published on an open source license. But the RISC-V implementations themselves, so like the processors that implement the RISC-V instruction set, they could be open source or they could be proprietary. There's both out there. So, if it says RISC-V, it doesn't just mean it's open source. You kind of have to look into it a little bit more detailed. But one important thing to note is we need open specifications in order to have open source implementations. So while RISC-V doesn't mean open source, we can't have open source chips without an open ISA. So you can't go and make an open source processor based on Intel or ARM because those are proprietary instruction sets and you wouldn't be allowed to do that legally. So the RISC-V International Organization, which is the nonprofit that governs the specs, they do have a security standing committee that was set up, I think, 2 years ago, I think around the time of Spectre and Meltdown. And there's currently 2 working groups that are working on extensions to the instruction set. So one is cryptographic extensions. The idea here is implementing the common operations that you need for various cryptographic routines in hardware. And then also the trusted execution environment. So this is the idea of like an enclave, which is inside of the processor that allows you to hold certain sensitive information. So these are both working on creating specifications for extensions to the ISA. Now that's just the specification, it's not the implementation. So there are other projects that are working on implementing those extensions as well. So one concrete example I wanted to give is there's interest right now in doing security research into how to mitigate timing attacks. So like with Spectre, I think it was 2 years ago, with Intel processors having the issue of branch prediction and being able to leak out information that you shouldn't have access to, it's become a big problem. So at Berkeley, one of the things that they had created was called Boom, which was Berkeley out of order machine. So this is an implementation of a RISC-V processor. And this is a recent paper that they wrote about their latest generation. And they talk about how the deployment of high performance superscalar out of order cores, which are the things that are susceptible to these timing attacks, has expanded a lot. So it's not just high-end servers and desktops, it's in mobile devices and edge devices as well. So the concern over these microarchitecture timing attacks, has increased a lot. Like, you hear probably every couple of weeks there's a new paper on some sort of timing attack. So one of the advantages that comes about from open source hardware is that we can implement these sorts of cores and then study them. This would be very difficult to do with a proprietary ISA. You wouldn't be able to probably share all the details of it. So by having the open instruction set allows these researchers to do research into how to hopefully mitigate and study and mitigate some of these timing attacks. Another project that's gotten some headlines is OpenTitan. So this is called the Silicon Root of Trust, or ROT. Some of you may have heard of Titan, which is a chip that Google makes for some of their products and servers that helps with some of the security aspects. So this is kind of a attempt to take that and then build upon it with a more open source foundation. So the idea here is there's different organizations, Google, lowRISC, which is a not-for-profit in the UK, they're all working together to how to implement a root of trust chip with open source tools. So an open source design both on the chip level and also in terms of the firmware and software that goes along with it. So this sort of thing could be used for pretty much any sort of device, so servers, routers, laptops, your smartphone, these new types of IoT devices. They're everywhere now. So one thing it can provide is the ability to be able to make sure you're booting the correct firmware and then it hasn't been tampered with. Another possibility is to be able to make sure that a device is legitimate, that it's not some sort of rogue device. Also, the ability to protect encryption keys. One of the big problems is where do you store the encryption key? So the idea here is that you could store the encryption keys inside of an OpenTitan chip, and it would allow you to have some confidence there that it couldn't be tampered with or extracted, and then provide authoritative, tamper-evident records of what's happened during the runtime of the chip. So this is a kind of a nice example here from their documentation of how OpenTitan differs from the current root of trust chips that are out there, like the Google Titan chip. And the big thing here that you see is that the chip design, which is sometimes referred to as RTL, or Register Transfer Logic, that's all open source. So the chip level design is all open source. And the packaging, so they've created a situation where they can keep track and have transparency at the board level, at the chip packaging level, at the chip design level. The only thing that's not covered by this is at the actual silicon fab. There are certain parts there that are not open, but as you can see, this is a big improvement over where things are right now with root of trust chips. One of the things I wanted to talk about too was FPGAs and the exciting developments that we've seen in terms of open source toolchains for FPGAs and how that relates to RISC-V. So if you're not familiar with an FPGA, it's a field programmable gate array. The idea here is you have a chip where it's just a sea or ocean of these logic elements that can be programmed. So the chip itself doesn't do anything, but by loading a design into it, it then reconfigures itself to be the hardware that you've designed, including a processor core. So we can actually load in the design of a RISC-V core, and the FPGA will reconfigure itself to actually be that digital design. And if you want to learn more about it, a really great talk from last year was from Megan Wachs at the Hackaday Super Conference. There's a link in the slides to it there. So kind of analogy to software, you know, when you write source code, you use a compiler to produce the binary that you use to execute. In the FPGA world, you have your hardware definition language, so Verilog or VHDL, and that gets synthesized by an FPGA software tool, and then finally transformed by a place and route tool into a bit stream, and that's what gets loaded into the FPGA. So typically these tools were all proprietary and they would come from the FPGA vendor. They'd be massive pieces of proprietary software. Like the one from Xilinx is like 40 gigabytes to install. It's crazy. So a few years ago, some really talented hackers, including Claire Wolf, started pioneering the ability to be able to use open source tools to program FPGA. So it started off with this smaller FPGA called the Lattice ICE40, which was really exciting at the time, but it's a smaller FPGA, so it limits the things that you can do with it. Then the bigger one from Lattice, ECP5, was supported with a project with a effort called Project Trellis from Dave Shaw. So yeah, some of the people who have been involved with this are Dave Shaw and Claire Wolf and a bunch of other people. There's a really awesome community of like open FPGA people. Definitely recommend following them on Twitter. So the ECP5 and the ICE40, both you can put different implementations of a RISC-V core into them, but they are somewhat limited. They don't have all the capabilities for higher speed peripherals that you may want. And that's what we find in FPGAs from Xilinx. So Xilinx is the market leader in FPGAs. So there's a bit of a gap there where the ECP5 and the ICE40 are nice, but they don't cover all the sorts of high-speed use cases that you might want to do. So another project called SymboFlow in Project X-Ray has put a lot of effort into supporting a portion of the Xilinx FPGAs called Series 7. And the support is almost there with these tools to be able to go from your source, like your Verilog or VHDL, all the way through to the bit stream that you load onto the FPGA with just open source tools. One of the big champions behind this is Tam Ansel, and he likes to say it's the GCC of FPGA. So kind of the parallel to how you use your open source tools to build programs. This is the kind of analogy, but for FPGAs. So this then becomes important if we want to build a trustable system using an FPGA. So at CCC last December, Bunny gave an awesome talk about him and Zobs were trying to build a device, a communication device where you could do some simple things like send text messages or potentially like sign, do cryptographic signatures with it. So kind of a constrained set of features, but they wanted to build a piece of hardware that was trustable. And one of the big issues here that Bunny identified was the issue of time of check, time of use. Like while you may be able to, you know, in a special lab, be able to verify that the chip is what you think it is, by the time it's actually in the user's hand, there's very little way for them to verify that it is what has been authenticated to be, because there's lots of places in between that can change. And he had a nice diagram in his presentation there of like all the different places where bad things can happen. So in all the way up to like, let's say you have the IC, the chip, and you go inspect it with some electron microscope, but then you still have to send it back to the user, and it could be interdicted at that point. So how do we get that time of check, time of use gap closed when it comes to hardware? You know, the software, it's easy. We can just do a hash and then we know that it's the same, the binary is the same thing as from the build server, but it's much more difficult when it comes to hardware. So one of the ideas here and what they're using in this project called Betrusted is an FPGA with a soft RISC-V core on it. So when I say soft core, that means a processor core design that's loaded into an FPGA instead of, you know, etched through lithography onto a silicon chip. And the nice thing here is if we're using an FPGA, then what the design of our processor is just essentially source code. It's that HDL like Verilog. So you can more easily synthesize that Verilog and have it closer to the user where they can have some greater level of trust that it is what they think it should be. And the two routes right now are using the ECP5 from Lattice or the Series 7 Xilinx FPGAs. And I was talking about before, that FPGA is kind of this sea of gates that we can configure to be what we want, including a soft RISC-V core. And one of the neat things that Bunny talked about here is, so the FPGA is a pretty uniform series of gates. And it's something that it would be very difficult for a malicious actor like at the fab to know what part of the FPGA to mess with, because they don't know exactly what our design is. And even if they did know what our design was, these FPGA tools have the ability to randomize what parts of the processor get put where in this grid of gates. So that makes it even more difficult for someone at the silicon foundry level to know what part of the die to mess with. So that's one of the ways that you can make it much more difficult for someone to be able to do a silicon level attack. And because we're using the soft core that's done in HDL like Verilog, and we're using open source FPGA toolchain, we actually can have much better confidence that the bit stream that we're loading into the FPGA is what we think it is. So one of the kind of like to leave you with one of the really exciting projects that's a little bit mind twisting, I think, is the idea of a trustworthy self-hosted computer. So there's this researcher named Gabriel Samlo, and he has a blog where he talks about his efforts to make a trustworthy, free, Linux-capable, self-hosting 64-bit RISC-V computer. So what does this mean? The idea here is that you have a system with an FPGA, and you run the FPGA tools on that system. So we load a RISC-V soft core into that FPGA, then we have Linux running on the RISC-V soft core, and then we have the open source FPGA tools running inside of Linux on top of that soft RISC-V core in the FPGA. So we can regenerate the whole system using the system. So he goes through some of the steps that he's gone through so far. And as the support for some of those higher end FPGAs improves with that project called SymbiFlow, we'll be able to target even higher end FPGAs with these open source tools. And ultimately, we're left here, his example that he's done so far is he uses one open source project called LiteX that lets you build system on chips in FPGA, and Rocket, which is a 64-bit open source implementation of a RISC-V processor. And this allows him to build a system that runs Linux and is self-hosting. So it's kind of an interesting thing there where the only thing you need to trust is this one system, and it can rebuild itself, which is quite interesting, I think. So that's all I have. I don't know if there's any questions. I mean, let me pop back. One thing I can't see here is if there's any questions in the chat.
There was one question regarding your slides, and then he said that yes, they would be made available later on as well.
Yeah, let me go back there. So if anyone wants to, that tiny URL right there, that will link to these Google slides here.
So friends, if you have any questions, please send them across via the Zoom chat. Drew, okay. How RISC-V can reduce timing attacks? Can it mitigate attacks like side channel?
Well, I think so RISC-V itself can't, because RISC-V is simply just a standard for the instructions that the processor implements. But the important thing here is because it's an open standard, anyone that wants to can do their own implementation. So like these researchers at Berkeley were able to do Sonic Boom, which is a RISC-V implementation. And it's a out of order superscalar processor, which means it is potentially susceptible to these timing attacks with speculation. So the important thing here was a lot of research, they use less complicated processors like in order processors, and those are not susceptible to these types of attacks. So having a superscalar out of order core means, potentially it could be susceptible to this, and they can do research around that. The other one that I didn't include in the slides, but if you check out the RISC-V International, they have the security working group, and they have monthly meetings. And there was a meeting, I think it was last week, that had a really interesting presentation from some researchers that were doing processor design to help mitigate side channel power analysis, which you've probably seen from Colin and the Chip Whisper. Pretty neat stuff there. So they're actually doing research into how to design a processor that's less susceptible to that. And I asked them, how does RISC-V help you with this? And they said it was really important for them to have an open ISA so that they could do the implementation however they wanted. So I think RISC-V itself doesn't do anything, but RISC-V enables more research than you would have with commercial ISAs.
All right. Is there any other question from the audience? So, well, Dhruv, I don't think there are any more questions from the audience, but thank you so much for sharing the ISA of RISC-V, and I'm sure a lot of people would definitely use it. So yeah, thank you again, Dhruv.
Yeah, thank you. Bye.
Thank you, everybody else. We would be recording this webinar and uploading it on our YouTube channel for future view. So thank you so much, everybody. And do join us for our hardwear.io conference, which is scheduled on the 1st and 2nd of October. Thank you, everybody. Bye.